Light begins its journey not in brightness but in near silence. For billions of years, photons travel unceasingly, indifferent to time, indifferent to the restless processes that give them origin. Against the backdrop of an expanding cosmos, each particle of light moves outward, slipping through voids that grow wider as the universe swells. What arrives in present-day observatories has traversed distances so immense that language folds under their weight. Yet the journey of these photons is not chaotic. It is precise, lawful, and rooted in the quiet rules of physics that govern the whole. Every observation begins with a single fact. Light carries information. It holds within its wavelength a record of the medium it has crossed, the temperature of the environment that once released it, and the stretching imposed by the expansion of space itself. In this way, light is both messenger and archive, bearing the oldest memories the universe permits to be seen. At the deepest reach of visibility stands the surface of last scattering, a faint glow released when the cosmos was only a few 100,000 years old. This glow is known as the cosmic microwave background, but in contemplative terms it is a wall of light that has drifted to us across more than 13 billion years. It fills every direction evenly, so smooth that it once seemed uniform. Yet on closer inspection it reveals small patterns, temperature ripples only a fraction of a degree, written across the sky like delicate embroidery. These ripples are not random. They are imprints of density variations in the early plasma, seeds of galaxies and clusters yet to form, visible yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. These ironies accompany every glance at the cosmic background. But before those photons could ever be free, the universe was opaque. In its early state, matter and radiation were bound tightly. Photons scattered constantly from charged particles, never able to travel far before colliding again. It was a fog so dense that vision as we know it was impossible. Only when the universe cooled enough for electrons to combine with nuclei, forming neutral atoms, did the fog clear. That event, known as recombination, marked the instant when photons decoupled from matter. They slipped loose from their former prison and began their uninterrupted flight outward. From that time forward, the universe became transparent. The light we detect today is therefore not the story of stars or galaxies, but the record of a plasma cooling into clarity. This moment of freedom is delicate in its precision. The background we see is not the first light created. It is simply the oldest light that has survived in transit. There were earlier radiations, far hotter, more energetic, but they could not endure the opacity of the primordial plasma. What arrives to us is not the beginning of time, but the earliest page left legible. Like mist thinning just enough to reveal a shoreline, then stopping, the surface of last scattering is both a revelation and a limit. It gives vision while denying all that lies beyond. It is a boundary not because there is nothing further, but because light from before that instant cannot reach us. The faintness of this background should not be confused with fragility. It is everywhere, and it is persistent. Even the noise of a local electronics or the crackle of cosmic rays cannot erase its presence. Sensitive instruments tuned to microwave wavelengths detect it without fail, a constant bath of radiation at a temperature of just under 3 degrees above absolute zero. It is the echo of an era when the universe itself glowed, when every cubic centimeter was filled with radiation now stretched into microwaves by cosmic expansion. To gaze into it is to see not a single source, but the entire cosmos as it once was. There is irony in how this limit appears as openness. The sky looks endless, yet its depth is bounded by the surface of last scattering. every direction one chooses points not to infinity, but to a wall of ancient light. What feels like endless extension is in fact a sphere, wrapped around us, defined by how far photons have been able to travel since recombination. We stand at the center of this sphere not because of privilege, but because every observer, no matter where located, sees the same horizon centered upon themselves, visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. Another irony rests in the comparison of time and distance. The photons from the cosmic background began their journey nearly 14 billion years ago, yet the region from which they came is today almost 46 billion light-years away. Expansion has carried it outward while the photons move toward us. In this way, what is most ancient in time is most distant in space. The light that left when the universe was young belongs now to regions receding faster than any hope of approach. The message is preserved, but the source has retreated irreversibly. The mystery of what lies beyond this wall of light persists. We know that earlier epochs existed, an even hotter plasma, inflationary expansion, quantum fluctuations that were stretched into macroscopic scales. Yet direct observation halts at the surface of last scattering. Beyond it lies only inference. Models and mathematics extend into that hidden domain, but no photon can carry its truth into our reach. Here is another irony. The most pervasive light in the cosmos is also a barrier. It reveals the early universe while concealing what came before, visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. Scientists refine instruments to read more from this glow. Minute variations in polarization, delicate patterns in angular distribution, correlations across scales, all become clues about conditions in the earliest instance. Yet the data remain fragile, vulnerable to interference from nearer sources, galactic dust, radio noise, instrumental calibration. Sometimes it is the silence, the subtraction of all foregrounds that matters most. From what is left, a picture emerges of a universe remarkably flat, remarkably uniform, with just enough irregularity to allow galaxies, stars, and eventually life. That such immensity emerges from such small fluctuations is another quiet irony. The cosmic background is therefore not a distant object but a universal presence. It is the faint residue of once unimaginable brilliance. It reminds us that the cosmos began in conditions where light could not travel freely, and that our vision of the past will always be limited by that fog's final clearing. It is both the first chapter of visible history and the closing door on what lies beyond. As one listens to the silence of space filled with photons that whisper of an origin forever receding, the edge of the observable universe appears not as a cliff or a boundary, but as a veil of light stretched thin across time. It is an edge only in appearance, a horizon where seeing ends but where the universe itself continues unbroken. Horizons define what is knowable, and in cosmology there is more than one. At first thought the horizon seems simple, a farthest distance beyond which nothing can be seen. Yet the universe offers several, each drawn not by walls or structures, but by the interplay of time, expansion, and the finite speed of light. The particle horizon is one such boundary. It marks the maximum distance from which particles of light could have travelled to an observer since the beginning of cosmic time. It is the ultimate limit of causal contact, the farthest edge of what has ever been in principle observable. The event horizon, in contrast, is a limit not of the past but of the future. It defines the boundary beyond which events can never influence the observer, no matter how long the cosmos continues. Between them lies the Hubble sphere, defined by the distance at which the recession velocity due to cosmic expansion equals the speed of light. Each horizon serves as a kind of marker, yet none coincides with the others. Horizons within horizons, boundaries layered like concentric shells, all invisible yet profoundly real. The particle horizon expands as time passes because light has had more time to travel. The older the universe becomes, the more distant regions can be seen. In this sense, the horizon recedes into the past but also broadens in space, enlarging the observable sphere. What is visible today was once hidden, not because it did not exist, but because light had not yet had time to cross the intervening void. Each added billion years extends the cosmic panorama, revealing new galaxies and background patterns, visible yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. These quiet ironies attend every horizon. The event horizon, by contrast, shrinks possibility rather than enlarging it. Due to the acceleration of expansion driven by dark energy, some regions that can be seen today will one day slip irretrievably beyond communication. Their light will continue to arrive, but new signals from them will never reach us. They will fade from influence, leaving their final messages to drift endlessly across space. This future limit is unsettling in its permanence. Even as the universe expands, the range of eventual contact diminishes. The irony is sharp. The longer the cosmos lasts, the less of it we will ultimately be able to reach. The Hubble sphere introduces another nuance. It is not a horizon in the strict sense, but a convenient measure of scale. At distances beyond the Hubble radius, galaxies recede faster than light due to the expansion of space. Yet their light can still be seen, because the photons were emitted when those galaxies were closer, inside the Hubble sphere, and the stretching of space allows them eventually to drift into our detectors. This underlines a subtle truth. Recession velocity is not motion through space, but motion of space itself. No galaxy is moving faster than light locally. Instead, the fabric of space between us and them is stretching so that their separation grows more rapidly than light can traverse, like mist thinning just enough to reveal a shoreline, then stopping. The Hubble sphere shows that the familiar rules of motion give way to cosmic context. Another irony arises in the comparison of these boundaries. The particle horizon today encloses a radius of about 46 billion light-years. The event horizon encloses a smaller sphere of about 16 billion light-years, defining the ultimate range of future communication. The Hubble sphere is smaller still, around 14 billion light-years. Each horizon gives a different answer to the question of how far the universe can be seen or reached. The numbers differ, yet each arises from the same simple fact. Light travels at a finite speed, and the cosmos expands, visible yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. The poetic detail of these multiple horizons is that none are physical walls. There is no edge, no barrier, no border to cross. Instead, the horizons are woven from geometry and time. They are limits of perception and influence, drawn by the constant speed of light and the changing scale factor of the universe. To imagine them is to imagine invisible shells, concentric spheres centered on every observer, shifting with time, stretching outward or tightening inward. Every point in space has its own horizons, and from each vantage the cosmos looks finite in reach but infinite in extent. Yet a mystery lingers in how these horizons overlap with theory. Cosmological models predict what lies beyond the particle horizon, regions similar to our own, filled with galaxies and matter, structured by the same physical laws. But because no signal can have crossed that divide, This assumption remains an article of inference. There could be variations, subtle or immense, that will never be detected. Cosmic variance ensures that our single observable sphere may not represent the totality. The universe may be homogeneous on average, yet the average is forever unmeasurable beyond our horizon. Here silence becomes more eloquent than data. The quiet ironies of horizons accumulate. They grow while shrinking. They reveal while concealing. They promise infinite symmetry while denying direct confirmation. Horizons within horizons, expanding and contracting across scales of time, leave observers suspended between openness and limit. It is a paradox of cosmic vision. To see farther is always to uncover another veil, to glimpse another boundary drawn not by matter, but by the mathematics of expansion. Instruments measure these boundaries indirectly, through redshift and background radiation, through faint galaxies stretched into whispers of light. Each detection affirms the reality of horizons without giving them a visible surface. There is nothing to photograph, nothing to map, nothing to cross. The edge is not a frontier, but a horizon defined by absence. It is a presence of limits rather than a thing in itself. In contemplative terms, horizons teach a patient truth. They remind that seeing is not the same as touching, and that reach does not extend as far as vision. They remind that the universe is both revealed and withheld at once. They remind that silence and absence are as instructive as light and signal. To dwell on horizons is to dwell on limits that shift as time flows, always receding, never vanishing, and always keeping the greater universe just beyond the line of sight. Photons that reach modern instruments from the most distant realms are not recent travelers. They began their journeys when the cosmos was young, when galaxies were only forming and quasars flickered in early darkness. These ancient messengers arrive today carrying histories stretched thin by expansion. To detect them is to peer backward in time, not merely across distance but into epochs that long ago ceased to exist. 13 billion-year messengers, faint and redshifted, whisper of conditions when the universe was still assembling its first great structures. The quiet irony is that what we see is not how those regions are now, but how they once were. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. The light of these early objects is profoundly altered. Wavelengths are stretched by the expansion of space itself, so that radiation emitted in the ultraviolet emerges at Earth as infrared, nearly invisible without precise detectors. What was once intense brilliance arrives as a pale shadow, fragile in its faintness. Observatories must sit atop mountains, orbit in space, or shield themselves from the atmosphere's warmth to register these signals. Each photon carries the mark of cosmic redshift, a measure of both distance and time. By reading that elongation, scientists reconstruct the age at which the photon set out. In this way, the light of galaxies becomes a clock, timing their emission and revealing the expanding geometry of the cosmos. Consider the galaxies seen at redshift greater than 10. These objects shone when the universe was less than 500 million years old. They are not like galaxies of the present, fully formed and settled. They are chaotic, compact, bursting with star formation. Their shapes are irregular, their starlight restless, their chemical content primitive. They remind us that cosmic order emerges only gradually. Yet even in their youth they radiated enough light to cross billions of years. That light captured now is all that remains of those early states. Like mist thinning just enough to reveal a shoreline, then stopping, these galaxies give a glimpse but not the continuation of the story. Quasars add another layer. Powered by supermassive black holes at their centers, They shine with an intensity that can outshine entire galaxies. The most distant quasars known lie at redshifts beyond 7, meaning their light began when the universe was less than 1 billion years old. Their brilliance is paradoxical. How could black holes so massive exist so soon after the origin of cosmic time? This remains an open mystery, for models of growth struggle to explain such rapid accumulation of mass. The photons we collect from these quasars are therefore both evidence and question. They illuminate the young cosmos while deepening uncertainty about how its structures formed so quickly. The path of these photons is long and uncertain. On their way they may have been bent by intervening masses, their course is altered by gravitational lensing. They may have been absorbed by clouds of hydrogen, creating dark troughs in their spectra known as Lyman alpha forests. They may have been scattered by dust or distorted by magnetic fields. Yet through all obstacles enough photons arrive to form an image, a spectrum, a signal. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. Each detection is a fragile survival of light against cosmic interference. The poetic detail is that these photons were released before Earth existed, before the Sun was born, before the Milky Way had completed many rotations. While oceans and mountains and continents have risen and vanished on our planet, the photons have continued steadily, their pace unchanged, their silence unbroken. When they began, the atoms that would one day make human beings were still locked in clouds of gas. Only after their long voyage could there be eyes and instruments to receive them. That such messages waited so long without expectation is a quiet wonder. There is a mystery in how many of these photons never arrive. Absorption, scattering, and expansion erase vast amounts of information. The sky that is visible is only a fraction of what was emitted. We see survivors, not the whole. The darkness between galaxies is filled with light that never reached us. It is another irony of observation. The more distant the source, the less of it remains visible, even as each fragment becomes more precious. Cosmic rionization complicates this picture. After recombination, the universe entered a long period of darkness before the first stars and galaxies formed. When they did, their ultraviolet light rionized the neutral hydrogen filling space, turning it transparent again. The moment of reionization is still uncertain, but high redshift quasars and galaxies suggest it occurred about 1 billion years after the beginning. The evidence appears in spectra, a sudden absorption trough called the Gunn-Peterson trough, revealing the presence of neutral hydrogen. Beyond that trough lies a universe still turning from opaque to transparent. Observing it is like catching a glimpse of dawn, when the sky is neither fully dark nor fully lit. Instruments such as the James Webb Space Telescope extend vision into these epochs. Its infrared eyes detect galaxies at the limits of redshift, revealing compact clusters of stars in the first few 100 million years. Each new discovery shifts the boundary of the observable outward, yet each also underscores the finite nature of what can be seen. There is always a further region hidden, always more light that will never be recovered. The universe offers glimpses, not completion. 3 quiet ironies repeat themselves here. Visible yet forever out of reach. The light shows past galaxies, but those galaxies are now vastly changed or gone. Only took 13 billion years to arrive. Messages that long predate humanity arrive just now, indifferent to whether they are seen. Silence carries more data than noise. The gaps, the missing photons, the dark troughs reveal as much as the light itself. These ironies are not rhetorical flourishes, but reflections of the observational reality. The analogy is one of archaeology on a cosmic scale. Excavating ruins reveals only fragments, broken stones that hint at structures long vanished. The ancient photons are similar fragments. They cannot rebuild the entire edifice of the early universe, but they reveal its outlines. They show that galaxies formed earlier than once thought, that quasars grew faster than models expected, and that the cosmos was transparent by the time it was 1 billion years old. The story is written in partial inscriptions, incomplete yet unmistakable. And yet mystery remains at the edge of these detections. How massive black holes grew so fast, how the first galaxies assembled, how the faint fluctuations of the cosmic microwave background became the luminous objects now seen. These are questions that endure. The answers may lie beyond the reach of light, hidden in regions from which photons can never return. Horizons frame not only what is seen, but also what will forever be unsaid. In that silence, the cosmos holds its deepest reserve. When the universe was very young, it was dense, hot, and filled with a plasma of photons, electrons, and nuclei colliding in constant exchange. In such a state, light could not travel freely, for every photon was quickly scattered by charged particles. The cosmos was opaque, not because of any barrier, but because of the restless interactions of its contents. As the universe expanded, it cooled, and when its temperature fell to about 3000 degrees Kelvin, a transformation occurred. Electrons combined with protons to form neutral hydrogen atoms, and in that instant the scattering slowed dramatically. Photons were no longer trapped in a fog of plasma, but could travel across space without constant interruption. This release is known as photon decoupling, and it produced the cosmic microwave background. Frozen decoupling, a transition from opacity to transparency, is the oldest visible memory of the cosmos. The photons released at recombination carry the temperature of that time, stretched by cosmic expansion into the microwaves we detect today, at a uniform glow of about 2.7 Kelvin. What appears smooth across the sky hides minute fluctuations, differences of only 1 part in 100,000. Yet those faint irregularities were enough to seed the great structures of the cosmos, the galaxies and clusters that later grew under gravity. What we call cosmic background radiation is therefore not only the earliest visible light, but also the foundation on which all later complexity was built. The quiet irony is that the largest structures of the universe began as the smallest variations, visible, yet forever out of reach, only took 13 billion years to arrive. Silence carries more data than noise. The poetic detail of recombination is that it was not instantaneous. It spread across time as the cooling progressed, lasting for many thousands of years. The surface of last scattering is not a sharp boundary but a layer, thickened by the gradual process of electrons binding with protons. Each photon that arrives today was released at a slightly different moment within that interval, giving the background a finite thickness. What is seen as a wall of light is in truth a fog dispersing over time, a veil thinning until photons could move unimpeded, like mist thinning just enough to reveal a shoreline, then stopping. The surface of last scattering reveals and conceals in equal measure. The study of the cosmic microwave background has become one of the most precise sciences in cosmology. Satellites such as COBE, BMAP, and Planck have mapped its temperature variations across the entire sky. These patterns form a statistical fingerprint of the early universe, revealing its density, composition, curvature, and age. From the delicate ripples in the radiation field, cosmologists infer the amount of ordinary matter, and dark energy. They read in the anisotropies the geometry of space itself, finding it remarkably flat on cosmic scales. The photons carry information not only about their moment of release, but about the invisible contents of the cosmos. Silence carries more data than noise. The near uniformity of the background is as significant as its small fluctuations. Yet even here uncertainty remains. The exact processes of reionization, the detailed physics of inflation that set the initial conditions, the true nature of dark matter and dark energy, all are hidden behind this frozen surface. The background is a record, but it is not a complete record. It is the first legible chapter, while earlier pages are lost to direct observation. The irony is that what seems like an origin is really a threshold. We see the universe not at its birth, but in its early childhood. Beyond that point lies a silence that only theory can explore. Another irony rests in the contrast between faintness and ubiquity. The radiation is weak, almost negligible compared to the brightness of stars and galaxies, yet it fills every direction with unwavering presence. Instruments tuned to its wavelength cannot avoid it. It is not a signal one must search for, but one that must be carefully subtracted to see anything else. The most pervasive background is also the quietest, an almost invisible glow that covers the sky without interruption. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. Observing the polarization of the cosmic microwave background adds another layer of subtlety. Polarization patterns arise from the scattering of photons at recombination, and later from gravitational waves imprinted during inflation. Detecting these patterns requires extraordinary precision, for they are faint, hidden among galactic dust and instrumental noise. Yet they hold the promise of revealing the earliest moments, the stretching of space itself in its first fractions of a second. Whether such signals can be unambiguously separated from foregrounds remains an open question. The quiet mystery is whether the cosmos will allow us to read that deeper imprint, or whether it will remain obscured behind the veil of noise. Foreground contamination is itself a poetic detail. Dust grains in the Milky Way emit at microwave wavelengths, creating signals that mimic the cosmic background. Separating the local from the universal becomes an art of subtraction, a search for silence beneath interference. The irony is that in order to read the oldest message in the universe, one must first erase the more recent emissions of one's own galaxy. What is nearest must vanish before what is most distant can be heard, like mist thinning just enough to reveal a shoreline. Then stopping, the subtraction of foregrounds leaves behind the faint but persistent cosmic memory. The surface of last scattering stands as both an origin and a boundary. It is the first light that can be seen, yet it hides what came before. Inflation, baryogenesis, the earliest quantum fluctuations, these lie beyond its curtain. The photons we observe are survivors, carrying only the record of plasma cooling into atoms. To look at them is to see both presence and absence, revelation and concealment. The cosmos gives its earliest visible moment but withholds its absolute beginning. The quiet ironies repeat themselves here with unbroken rhythm. Visible, yet forever out of reach. The background is everywhere, but the conditions it depicts are gone. Only took 13 billion years to arrive. The glow that now appears ordinary has travelled across almost the entire history of the cosmos. Silence carries more data than noise. The near uniformity, the faintness, the absence of signal speak more profoundly than the brightness of stars. These truths, repeated like soft echoes, are the essence of the cosmic microwave background. The frozen decoupling is therefore both an event and a metaphor. It is the liberation of light from matter, the moment when visibility became possible. But it is also the first boundary of observation, the horizon where knowledge halts and mystery deepens. To contemplate it is to stand at the threshold of cosmic history, gazing upon the earliest visible glow while sensing the silence that lies beyond. In that silence the universe holds its deepest beginnings, unrevealed, untouched, and perhaps unreachable. Every observation of the distant cosmos is shaped by the stretching of light. As the universe expands, the wavelengths of photons grow longer, shifting toward the red end of the spectrum. This effect, known as cosmological redshift, transforms brilliant radiation into faint traces. A photon born in the ultraviolet can arrive in present detectors as infrared, its journey marked not by distance alone, but by the stretching of the space it traverses. Edges written in redshift are the boundaries of visibility, drawn by how far light has been shifted out of detectable ranges. The irony is simple. The more the universe reveals, the more it also erases, turning brightness into dimness, detail into blur, information into silence. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. The Hubble-Lemaitre law formalizes this relationship. Galaxies recede from one another at speeds proportional to their distances, not because of motion through space, but because space itself grows. The law is expressed in velocity per distance, a constant that describes the expansion rate. Observations of spectral lines stretched to longer wavelengths give redshifts, and from redshifts comes distance. In this way, astronomers map the universe by measuring how much light has been shifted. The sky becomes a record not only of position but of time, each object showing its age through the degree of its redshift. The universe does not place labels on its structures. The shifting of light is the label, a quiet and universal code. For galaxies nearby, the shifts are small, spectral lines displaced only slightly. For galaxies at great distances, the lines move so far that only specialized instruments can register them. At the highest redshifts yet observed, light has been stretched more than tenfold. Some galaxies are so distant that their light is shifted completely out of the visible band, requiring infrared detectors cooled to cryogenic temperatures. Without such tools, those galaxies would remain unseen, hidden not by distance but by transformation of their light. The poetic detail is that every telescope is designed to match the stretch of the cosmos, choosing its instruments to meet the universe halfway. The mysteries deepen as redshift approaches extremes. What happens when light is stretched beyond any practical ability to detect? There are galaxies whose light has already crossed that threshold, receding so swiftly that their signals will never arrive. The event horizon marks this limit, and beyond it no new photons can reach us. Yet even within the observable region, expansion erases much of what could be known. The universe is not withholding out of secrecy, but out of law. Light travels at a constant speed, space expands relentlessly, and the two together impose boundaries on vision. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. There is irony in how these immense distances are measured with the smallest of features. A spectral line, a narrow dip or peak in the brightness of a star or galaxy, becomes the ruler of the cosmos. The hydrogen line, the calcium triplet, the oxygen doublet, tiny markers in spectra become mileposts billions of light-years long. The largest scales of the universe are mapped by the thinnest of notches. This is science by whispers, where faint patterns stand in place of monuments. The edges of the observable universe are written not in towering structures, but in stretched shadows of atomic transitions. Another quiet irony is that while galaxies recede faster with distance, the light they emitted in the past can still reach us. Galaxies now beyond the Hubble radius can be seen because their photons were released when they were closer. The image we receive is ancient, a fossil of earlier conditions. To look far is to look back. We do not see the present universe but the record of its youth. This fact is sometimes described as a look-back time, measured in billions of years, but the commoving distance of those galaxies is far greater because expansion has carried them away during the photon's long flight. Like mist thinning just enough to reveal a shoreline, then stopping, red-shifted galaxies show us what once was but not what now is. The poetic resonance of redshift is that it ties vision to time. Every faint smudge on a detector is not a contemporary neighbour but a relic of an earlier cosmos. The deeper the redshift, the younger the universe was when the light was emitted. Thus, telescopes become time machines, not in fantasy but in the literal sense that looking outward means looking backward. To study the edges of observation is to study the earliest eras, not by revisiting them, but by intercepting the photons that have travelled unbroken across cosmic history. The mystery persists in how far this method can be extended. Current instruments can measure galaxies at redshift greater than 10, but beyond that the light becomes faint, absorbed, and stretched beyond reach. There may be galaxies and stars that formed earlier, their photons still travelling, but their signals will be drowned in noise or hidden in wavelengths our detectors cannot yet reach. The silence is not absolute absence, it is potential information beyond grasp. The irony is that while the universe may be infinite, our perception of it will never be. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. Standard candles and standard rulers add subtlety to redshift measurements. Supernovae of type Ia, with consistent peak brightness, provide distances when their apparent brightness is measured. Baryon acoustic oscillations, imprinted in the distribution of galaxies, serve as rulers across cosmic scales. These methods calibrate redshifts into distances, ensuring that the stretching of light is not merely a curiosity but a quantitative tool. Yet each method carries uncertainties: dust obscuration, intrinsic variation, cosmic variance. Even here, silence carries more data than noise, for the gaps and scatter in the data reveal as much about the limitations of observation as the signals themselves. The ironies accumulate in rhythm. To see farther is to see dimmer. To measure distance is to measure loss. To read the history of galaxies is to read only their youth, not their current state. These truths are woven into the fabric of observation. The universe does not grant complete vision but partial glimpses, written in redshift. The edges are not abrupt walls but transitions into invisibility, where light has been stretched beyond sight. Thus, edges written in redshift are not literal borders, but gradual dissolutions of visibility. Each photon lengthened, each wavelength displaced, each detail fading into silence. To look at the most distant galaxies is to see them dissolve as their light drifts into unobservability. The cosmos writes its limits not in darkness, but in elongation, in the stretching of light until it becomes undetectable. It is not that the galaxies are gone, but that their light has been transformed beyond our reach. The universe speaks, and in speaking it also fades, leaving boundaries drawn in red. To contemplate the edge of the observable universe is also to confront the difference between how far back in time we can see and how far away those regions actually are today. Light does not travel instantaneously. It moves at a constant speed, and in a universe that expands, this constancy creates an irony. The further we look, the older the light, and the more distant the emitting sources become in the intervening billions of years. The concept of look-back time is a measure of how long a photon has been travelling before it reaches us. If the photon began its journey more than 13 billion years ago, its look-back time is 13 billion years. but the region from which it came is not 13 billion light-years away today. Expansion has carried it far beyond that. Its co-moving distance, the distance accounting for expansion, is nearly 46 billion light-years. In this way, time and space diverge, leaving observers caught between two measures of reality. The distance that grows is a horizon of paradox. The poetic detail is that every photon is a bridge across eras, arriving in the present but originating in conditions now remote. The light of a galaxy that shines at redshift 10 set out when the cosmos was only a few 100 million years old. That same galaxy has since moved unimaginably far from us, drawn outward by the growth of space itself. To look at it is to see not what it is but what it was. The irony is soft but persistent. Every glance at the sky is a glance at memory, never at the present. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. The Hubble diagram illustrates this divergence. When plotted, distances inferred from brightness and redshift do not align along a simple straight line, but curve, reflecting the changing rate of cosmic expansion. In earlier epochs, the expansion was slower, governed by matter and radiation. In more recent epochs, it has accelerated, driven by dark energy. Look-back time grows steadily with redshift, but co-moving distance grows faster, revealing how much space has stretched during the light's travel. The quiet irony is that the very act of observing the past reminds us how distant the present has become. Another layer of subtlety emerges in the concept of light travel distance, the naive measure of multiplying the speed of light by the age of the photon's journey. That distance yields numbers around 13 billion light-years, corresponding to the age of the universe. Yet the true co-moving distance is far greater. The expansion of the universe is not merely a backdrop, but a participant in the measurement. The fabric of space does not remain static while photons cross it. It stretches under them, elongating their paths and carrying the sources farther outward. To think of the distance as fixed is to miss the essential truth. The cosmos grows even as light moves. The poetic analogy is of a traveller walking across a meadow while the meadow itself expands beneath their feet. No matter how far the traveller walks, the destination moves farther away. The progress is real, but the separation increases faster than the stride, like mist thinning just enough to reveal a shoreline, then stopping. Light reveals the past but cannot deliver the present. The distance grows with time, and the more faithfully we measure it, the more evident becomes the irreducible gap between vision and presence. The mystery deepens when we attempt to define the true size of the observable universe. Depending on which measure is chosen, look-back time, light travel distance, co-moving distance, the answer changes. Each is valid, each grounded in physics, yet they offer different perspectives. There is no single number that captures both the age of the light and the present position of the source. The irony is that the simplest question, how far away is the most distant galaxy, has no single answer. It depends on whether one means then or now, path or distance, memory or presence, visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. Measurements of high redshift galaxies illustrate this disjunction. A galaxy whose light we see today as it was 600 million years after the beginning is not only ancient in time but remote in space. Its present location is beyond 40 billion light-years away, receding ever faster. We cannot interact with it, cannot send a signal to it, cannot hope for reciprocity. The light we see is its farewell, an archive of what once was. The distance that grows ensures the message can be received but never answered. The irony extends to every region of the observable universe. All are visible only as they were, not as they are. The farther one looks, the greater the distortion of time. The present cosmos, with its evolved galaxies and vast structures, is inaccessible to direct sight. Our instruments show us the ancient universe, while the contemporary one slips silently beyond reach. This is not a limitation of technology but of law. No detector can see the present at vast distances. The sky is a museum of fossils, its exhibits glowing faintly across time. Cosmologists use models of expansion to reconstruct what those distant regions are like today. By combining redshifts, brightness measurements, and cosmic parameters, they calculate the current positions of galaxies and clusters. But these reconstructions remain theoretical extrapolations. They are grounded in evidence but not in direct observation. The irony is that while we can calculate with confidence the present positions of galaxies, we can never confirm them by light. They are forever hidden behind the slowness of photons and the quickness of expansion. This divergence of time and distance has practical consequences for our understanding of large-scale structure. The cosmic web we map with telescopes is not the web as it exists today, but as it existed billions of years ago. The filaments of galaxies, the clusters, the voids, they're evolving continuously, shifting under gravity and expansion. Our maps are mosaics of different epochs, layered into a single view. It is as though one could look at a forest and see some trees as saplings, others as full-grown, others as fallen all at once. The sky is such a composite, a mixture of pasts presented as if simultaneous. The poetic detail is that even local galaxies, though nearer, are seen as they were in the past. The Sun itself is seen 8 minutes ago, the nearest star over 4 years ago, the Andromeda galaxy more than 2 million years ago. The principle is universal. Vision is always of memory. The irony lies not only at cosmic edges but at every scale. What is seen is always delayed, always historical. No image is present. Every sight is a look back. The three ironies echo through this contemplation. Visible, yet forever out of reach. The light of distant galaxies shows their past but not their present. Only took 13 billion years to arrive. Signals that predate Earth itself are captured just now, indifferent to the weight. Silence carries more data than noise. The gaps, the erasures, the absences tell as much as the signals themselves. These refrains are the rhythm of cosmic observation, recurring without end. Thus, the distance that grows is not an error of perspective, but a fundamental property of an expanding universe. Time and space diverge, and the further we see, the greater the gulf becomes between what is observed and what exists now. At the horizon of vision stands not an edge but an ever-widening gap, a reminder that the universe is both revealed and withheld. In the quiet patience of photons stretched across billions of years lies the truth. Every sight of the cosmos is a sight of what no longer exists, a memory preserved in light, carried across a distance that only grows. At the edge of the observable universe, where light is faint and redshift extreme, one finds quasars burning with improbable brilliance. These ancient beacons are powered by supermassive black holes, engines of gravity that draw matter inward and convert infall into radiant energy. Though they lie billions of light-years away, their luminosity is so intense that it outshines entire galaxies. Quasars serve as distant lighthouses, guiding perception into the early epochs of cosmic time. At redshifts greater than 7, they reveal a universe less than 1 billion years old, still in the midst of transition from opacity to transparency. Quasars at the threshold of vision remind us that even in youth, the universe held extraordinary extremes. Their light, stretched across billions of years, carry spectra rich with absorption lines, silent testimony to the hydrogen clouds they encountered on their journey. These features, known as the Lyman Alpha Forest, record the state of intergalactic gas at different epochs. Each dip in the spectrum is a shadow cast by hydrogen atoms absorbing ultraviolet photons. Taken together, they form a chronicle of cosmic ionization, the era when the first stars and galaxies ionize neutral hydrogen, allowing transparency to return. The quiet irony is that darkness reveals light, for the absorption troughs in quasar spectra show more about the universe than the quasars themselves. Visible, yet forever out of reach, only took 13 billion years to arrive. Silence carries more data than noise. The poetic detail is that these quasars shine from galaxies that were still assembling. Around the central black hole, matter spirals in luminous accretion disks, while outflows of gas form jets stretching thousands of light years. Yet the host galaxies are irregular, clumpy, filled with young stars and dust. The juxtaposition of youthful galaxies and ancient black holes is striking. How did such massive black holes form so quickly in so young a cosmos? The mystery lingers without firm resolution. Models of gradual growth struggle to explain their existence. Perhaps seeds of unusual mass were created in the earliest epochs, or perhaps accretion was more efficient than expected. But the truth remains concealed behind the horizon of direct evidence. The irony deepens when considering that these most luminous objects mark the limits of visibility. They can be seen because they are bright, yet most galaxies of the same epoch remain invisible, too faint to register on detectors. Thus, what we know of early cosmic structure comes disproportionately from the outliers, the extraordinary rather than the ordinary. It is as though the history of a civilization were reconstructed only from its fires, not its homes. Quasars illuminate, but their light is biased. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. Quasar spectra also contain the Gunn-Peterson trough, an absorption feature created when neutral hydrogen in the intergalactic medium blocked ultraviolet photons. The appearance of this trough in high redshift quasars signals the tail end of ionization. Before this transition, the cosmos was filled with neutral gas, scattering and absorbing light. After it, the gas was ionized and transparent. Thus, quasars serve as probes of a dawn we can otherwise barely glimpse, like mist thinning just enough to reveal a shoreline, then stopping. They mark the transition from darkness to light, from opacity to transparency. The poetic resonance of this transition is profound. For hundreds of millions of years after recombination, the cosmos contained no stars, only dark matter halos and cooling gas. When the first stars ignited, they filled space with ultraviolet radiation, gradually ionizing the hydrogen. Galaxies formed, clusters grew, and transparency spread. Quasars, emerging during this epoch, were both participants and witnesses, their radiation both influenced by and influencing ionization. To see them is to see the universe remaking its own transparency, step by step, until light could move freely again. The mystery of quasar formation persists despite careful observation. How could black holes with masses of 1 billion suns form so quickly? Conventional models of stellar collapse and gradual accretion suggest slower growth. Exotic explanations are proposed but remain uncertain. Perhaps direct collapse of massive gas clouds seeded them, or perhaps mergers of dense objects accelerated growth. But the truth remains unconfirmed, hidden in epochs beyond present visibility. The irony is clear. The brightest lights of the young universe conceal more than they reveal. There is another irony in their role as markers of distance. Because quasars are so luminous, They can be seen across the cosmos, making them useful as reference points for mapping large-scale structure. Yet their variability, their complex physics, and their evolution across time complicate their use as standard candles. They guide vision but resist easy calibration. The very properties that make them visible also make them unreliable for precise measurement. They are lighthouses, but their beams flicker and change. Still, their presence is indispensable. Quasars open a window onto an era otherwise hidden. They provide the most distant spectra, the deepest absorption lines, the clearest evidence of reionization. Without them, the early universe would be far more silent. Their light may be biased and enigmatic, but it is also the only light bright enough to reach us from such remoteness. They embody the irony of observation. The cosmos reveals itself through its exceptions, visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. The poetic detail is that quasars, though among the earliest objects observed, still exist today in quieter forms. Active galactic nuclei, blazars, and Seyfert galaxies are their modern descendants, powered by the same engines of accretion. The distant quasars are not extinct phenomena, but youthful versions of processes still at work. To look at them is to see not only the past, but also the persistence of cosmic mechanisms. The difference is one of scale, of intensity, of circumstance. The quiet engines of today's galaxies are echoes of the roaring quasars at the edge of visibility. Thus, quasars at the threshold remind us that the universe, even in its earlier stages, produced extremes of power and brightness. They remind us that the most distant light is also the most enigmatic, that the brightest sources can cast the deepest shadows of uncertainty. They remind us that observation at the edge is shaped by both presence and absence, by both illumination and concealment. Quasars guide perception outward, but they do not resolve all mysteries. They are luminous riddles, ancient lighthouses whose beams travel across cosmic time, arriving as fragments of stories still incomplete. The earlier structures we see, whether faint galaxies or brilliant quasars, carry imprints of a process that occurred even earlier and on scales beyond direct sight. This process is inflation, the rapid expansion that is thought to have taken place in the first tiny fraction of a second. In less than the blink of an eye, space expanded enormously, stretching quantum fluctuations into seeds of cosmic structure. Though inflation itself cannot be observed directly, its traces linger in the flatness of space, in the uniformity of the cosmic microwave background, and in the delicate patterns of density variations. These signatures form the silent fingerprint of an epoch that lies far beyond the surface of last scattering. Inflation's trace is subtle yet pervasive, present in every map of the sky, written in the statistics of temperature fluctuations and the geometry of cosmic structure. One of the most remarkable consequences of inflation is the apparent flatness of the universe. Without inflation, the cosmos might have curved dramatically, either collapsing back on itself or expanding too quickly for structure to form. But inflation stretched any initial curvature so thin that today the universe appears flat to extraordinary precision. This is not a flatness of 2 dimensions, but a flatness of 3-dimensional space on the larger scales, where parallel lines do not converge or diverge. The poetic detail is that flatness itself is invisible. One cannot look at the sky and see its geometry. It emerges only from measurements, from the way fluctuations appear across different scales. The irony is that what seems like an obvious emptiness, the absence of curvature, is itself profound evidence of an event that occurred before any light was released. Uniformity is another trace. The cosmic microwave background is nearly the same temperature in every direction. varying by less than 1 part in 100,000. Without inflation, regions of the sky separated by vast distances would never have been in causal contact, never able to exchange information or energy, and yet they show the same conditions. Inflation solves this horizon problem by positing that all regions were once close enough to interact before being driven apart by expansion. What looks like sameness across the sky is not a coincidence, but a consequence of immense stretching. The quiet irony is that uniformity, which seems like lack of information, is in fact information of the deepest kind. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. Even more delicate is the pattern of fluctuations in the microwave background. Inflation stretched quantum ripples to cosmic scales, leaving behind tiny differences in density. These differences grew under gravity into galaxies and clusters. The statistical distribution of these fluctuations matches predictions of inflation with extraordinary accuracy. In this way, the randomness of the quantum world became the architecture of the universe. Like mist thinning just enough to reveal a shoreline, then stopping, inflation's trace is visible not in direct sight, but in the patterns that only emerge through careful measurement. The poetic resonance is that something so brief and unobservable has shaped everything that followed. The mystery of inflation is that while its traces are clear, its mechanism remains unknown. What field or force drove it? What stopped it? Was it a single event or part of a larger multiverse? These questions remain unanswered. Different models of inflation propose different scenarios, but no consensus has been reached. The irony is that we have compelling evidence of something we do not yet understand. Inflation explains what we see, but hides how it occurred. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. The search for inflation's deeper signature focuses on polarization of the cosmic microwave background. Certain patterns, called B-modes, could be caused by gravitational waves generated during inflation. Detecting them would provide direct evidence of the stretching of quantum fluctuations. Yet the signals are faint, easily masked by galactic dust. Instruments have reported hints, but none have been confirmed. The silence persists. It is possible that the signal exists but is too faint to be distinguished from foregrounds. The irony is that the most powerful expansion in cosmic history may have left only the faintest of echoes. Inflation also leaves uncertainty about what lies beyond the observable universe. If space was stretched so greatly, then regions beyond our horizon may be vast, perhaps infinite, yet we cannot see them, cannot confirm their existence. Our observable sphere is only a patch of a much larger whole. The poetic detail is that inflation implies we live inside a fragment of something immeasurable. Like a shoreline glimpsed through mist, the visible cosmos suggests, but does not reveal what extends beyond. The mystery is whether that larger universe is similar to our own or different in ways we cannot imagine. There is irony in how inflation transforms the smallest scales into the largest. Quantum fluctuations, ordinarily confined to microscopic realms, became the seeds of galaxies spanning millions of light years. The tiniest uncertainty became the foundation of structure. Silence carries more data than noise. The faintest ripples of the early universe carried the blueprint of everything to come. The cosmos is built from whispers, its grandeur rooted in the subtlest of fluctuations. Inflation's trace is therefore both fact and riddle. We see its consequences but not its cause. We measure its fingerprints but not its hand. It solved problems of curvature, horizon and structure, yet it left behind mysteries as profound as those it answered. In contemplative rhythm we return to the same ironies, visible, yet forever out of reach. The evidence is everywhere, but the event itself is hidden. Only took 13 billion years to arrive. The traces of a moment less than a trillionth of a second long endure across cosmic time. Silence carries more data than noise. The uniformity, the absence of curvature, the faint fluctuations say more than any brightness could. Thus, inflation stands as the deepest horizon of inference. It is not seen directly, nor will it ever be. It is reconstructed from the traces left on light, on structure, on geometry. It is the quiet expansion behind all other expansions, the moment when the universe was set on its path. To contemplate inflation is to contemplate the paradox of evidence without sight, of fingerprints without a hand. It is a reminder that the cosmos carries within it events that can be known only indirectly, and that knowledge at the edge is always partial, always incomplete, always written in silence. As the universe expands, its fabric does not merely stretch, it accelerates. This acceleration is traced to what cosmologists call dark energy, a form of energy that permeates space itself and drives galaxies apart faster with time. The quiet pull of dark energy is not a pull at all in the ordinary sense. It is the opposite of attraction, a steady pressure that resists gravity and dominates on the larger scales. The evidence is clear from observations of distant supernovae, from the distribution of galaxies, and from the detailed patterns in the cosmic microwave background. Together they reveal that the universe is not slowing down as once expected, but is expanding more quickly as time passes. The irony is gentle but profound. The more the universe contains, the more it seems to accelerate away from itself. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. The discovery of dark energy in the late 20th century transformed cosmology. Supernovae of type Ia, exploding white dwarf stars with near-uniform brightness, were used as standard candles to measure cosmic distances. When astronomers compared their distances to their redshifts, they found the expansion was not decelerating but accelerating. What began as a surprising anomaly became the foundation of a new understanding. Most of the cosmos is not matter, visible or dark, but energy that we cannot detect directly. The poetic detail is that the brightest explosions in the universe revealed the faintest presence. Dark energy is modelled as a cosmological constant, a uniform energy density that fills space and does not dilute as the universe expands. Alternatively, it could be a dynamic field, slowly evolving in time. Observations so far are consistent with the cosmological constant, but uncertainty remains. The mystery is what dark energy truly is, for no known particle or field accounts for it. It may be a property of the vacuum itself, or it may be something altogether unknown. The irony is sharp. The force that shapes the future of the cosmos is the least understood. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. The effects of dark energy are not uniform across scales. Within galaxies and clusters, gravity binds matter tightly enough to resist cosmic acceleration. It is only on scales of hundreds of millions of light-years that the expansion dominates. This creates a universe with two natures, locally stable, globally restless. Stars orbit steadily within galaxies while the galaxies themselves drift apart at increasing speeds. Like mist thinning just enough to reveal a shoreline, then stopping. Dark energy defines a limit to connection. What is close remains bound. What is distant recedes forever. One poetic irony is that dark energy ensures the night sky will become emptier with time. Galaxies beyond the local group will eventually cross the cosmic event horizon, receding so quickly that their light will no longer reach us. In trillions of years, observers in the Milky Way may see only their own galaxy, unaware that the wider cosmos once existed. The abundance of light we see now is temporary, a momentary window before acceleration erases it. The cosmos reveals itself generously only for a finite epoch. Visible, yet forever out of reach, only took 13 billion years to arrive. Silence carries more data than noise. Another irony lies in the balance of energy components. Ordinary matter makes up less than 5% of the total density of the universe. Dark matter, unseen but inferred from its gravitational effects, contributes about 25%. Dark energy accounts for the remaining 70%. The cosmos is dominated by what cannot be directly observed. The irony is relentless. The more precise our measurements, the clearer it becomes that most of reality is hidden. What is known is the exception, not the rule. Cosmologists attempt to probe dark energy through surveys of galaxies and clusters, mapping their distribution across billions of light years. Subtle patterns, called baryon acoustic oscillations, serve as standard rulers for cosmic expansion. By tracing how these patterns evolve with redshift, the history of acceleration can be reconstructed. Yet the results so far remain consistent with a constant density, a cosmological constant. The silence of variation is itself information. Silence carries more data than noise. If dark energy changes, it does so too slowly for current instruments to detect. The mystery persists. Why does dark energy have the value it does? If it were larger, galaxies might never have formed, torn apart by acceleration. If it were smaller, the universe might have collapsed under gravity. The observed value appears finely tuned, balanced between extremes. Whether this is coincidence, necessity, or evidence of deeper laws remains unsolved. Like mist thinning just enough to reveal a shoreline, then stopping, our understanding halts at the boundary of explanation. The irony of dark energy is that it determines the ultimate fate of the cosmos. If its density remains constant, expansion will continue to accelerate, carrying galaxies farther apart until each becomes isolated. If it increases, space itself may tear in a big rip. If it decreases, expansion may slow. The evidence so far points toward continued acceleration, an ever lonelier future. The universe that now appears vast and filled with galaxies will become sparse, its horizons shrinking in influence even as they grow in size. The poetic detail is that acceleration does not alter what we see today, but what we will never see tomorrow. The galaxies visible now remain visible for a while longer, their photons still en route, but their future light will fail to arrive. The present sky is thus a temporary gift, a fleeting openness before the silence of horizons deepens. In this way, dark energy writes the destiny of visibility itself. In meditative rhythm, the three ironies repeat. Visible, yet forever out of reach, galaxies now shining will one day vanish beyond the horizon. Only took 13 billion years to arrive. The light we see today is the last we may ever receive from some sources. Silence carries more data than noise. The absence of change in dark energy's density speaks as loudly as any variation would. These refrains are woven into every discussion of acceleration, each echoing the stillness of cosmic inevitability. Thus, the quiet pull of dark energy is not pull but dispersal, not attraction but separation. It governs the largest scales while leaving smaller ones intact. It is both presence and absence, explanation and mystery. It ensures that the cosmos will never be static, that the edge of the observable universe will always drift outward, while what lies beyond recedes into permanent silence. To contemplate dark energy is to accept that most of the cosmos is both known in effect and unknown in essence. It is to rest in the paradox of evidence without understanding, of destiny written in expansion that can be measured but not explained. At the faint limits of vision, where galaxies blur into smudges and redshift stretches light until it nearly dissolves, observation depends not on sight alone, but on the careful measurement of echoes. Measuring in faint echoes means turning small fragments of signal into knowledge of structures that can never be visited. Photometry gathers the total light from distant sources, while spectroscopy spreads that light into lines and bands that reveal composition, motion, and age. Each photon is precious, for few arrive from such distances. Long exposures lasting hours or even days accumulate enough to form a pattern. The irony is clear. The vastest scales of the universe are mapped by the faintest drops of light, visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. Spectroscopy is the most powerful tool, for in the separation of light lie details otherwise invisible. A faint galaxy at redshift 10 reveals its presence by the displacement of spectral lines, telling us both how far and how long its photons have travelled. Absorption lines from intervening gas clouds punctuate the spectrum, turning absence into data. The Lyman alpha forest, with its countless dips, speaks of hydrogen spread thin across intergalactic space. Each trough is a silence that becomes evidence. The poetic detail is that absence of light carries more meaning than its presence. The universe speaks as much through what is missing as through what is given. Photometry, though less precise, allows the detection of sources too faint for detailed spectra. By comparing brightness in different filters, astronomers infer redshifts and estimate distances. These photometric redshifts are not exact, but they extend maps deeper than spectroscopy alone could reach. The irony is that the most uncertain measures sometimes provide the broadest view. Photometry paints the background, spectroscopy sharpens the details, and together they form the mosaic of cosmic structure. Standard candles and standard rulers serve as calibrations for these measurements. Type Ia supernovae provide candles, their consistent luminosity giving distances when their apparent brightness is measured. Baryon acoustic oscillations provide rulers, the imprints of primordial sound waves frozen into the distribution of galaxies. These features act as yardsticks across billions of light-years, anchoring redshifts to physical scales. Yet each method has uncertainties. Supernovae vary slightly, dust obscures, and intrinsic differences complicate their use. Acoustic oscillations require vast surveys to detect subtle patterns. The irony is that precision emerges not from clarity, but from complexity managed carefully. At the faintest limits, noise becomes a dominant presence. Detectors register not only photons from distant galaxies, but also random fluctuations, instrumental artifacts, and foreground emissions from nearer sources. Separating signal from noise is an art of subtraction, a process of removing what is known to isolate what is unknown. In cosmic microwave background studies, for example, galactic dust must be modelled and removed to reveal the primordial pattern. In galaxy surveys, stars from the Milky Way must be filtered out to leave behind distant objects. Like mist thinning just enough to reveal a shoreline, then stopping, noise removal exposes glimpses of the deeper cosmos but never the whole. The poetic detail is that some signals exist at the very threshold of detection, barely distinguishable from randomness. A single pixel brighter than expected, a faint line in a spectrum, a statistical excess across many images, these are often the beginnings of discovery. The difference between a real galaxy and an artifact can be vanishingly small, decided only after careful repetition and cross-checking. The universe does not announce itself boldly at its edges. It whispers, and the listener must learn to hear. The mystery arises in the limits of instruments themselves. Telescopes can grow larger, detectors more sensitive, exposures longer, but there will always be a horizon where photons are too few, too stretched, too faint to be distinguished from background. Beyond that horizon lies silence, not because nothing exists, but because observation fails. This is the quietest irony, that our knowledge is bounded not by imagination but by photons, by their scarcity, their faintness, and their loss in transit. Visible, yet forever out of reach, only took 13 billion years to arrive. Silence carries more data than noise. Foregrounds complicate measurement further. Earth's atmosphere glows in infrared, adding unwanted light. The Milky Way emits radio waves and dust radiation, filling detectors with local signals. Even planets and satellites reflect and emit contaminating observations. To measure the most distant light, astronomers must remove the closer. The universe is hidden not only by distance but also by proximity. The irony is that what is near often conceals what is far. Gravitational lensing adds another subtle complication, but also a gift. Massive clusters of galaxies bend light from more distant sources, magnifying and distorting them into arcs and multiple images. These lenses extend vision, revealing galaxies too faint to see otherwise, but they also distort, complicating the reconstruction of original shapes. The poetic detail is that gravity itself becomes a telescope, bending space into a natural instrument. Like mist thinning just enough to reveal a shoreline, then stopping, lensing allows glimpses beyond natural limits, though never without distortion. Cosmic variance is another unavoidable limit. Because there is only one universe to observe, and only one observable region, statistical measures are limited by sample size. We cannot average over multiple universes. The sky we see is both representative and unique, a single realization of cosmic probability. This limitation is not a failure of instruments, but of reality itself. The mystery is whether our observable patch truly reflects the whole. Silence carries more data than noise, for the absence of other universes to compare against is itself a reminder of our bounded perspective. Three soft ironies echo through the practice of faint measurement, visible yet forever out of reach. The light we capture is ancient, its sources transformed or vanished. Only took 13 billion years to arrive. Photons waited across cosmic time to register as faint traces on a detector. Silence carries more data than noise. What is absent, what is subtracted, what is missing reveals as much as what is recorded. These refrains guide observation, repeating like gentle reminders in the stillness of the cosmos. Thus, measuring in faint echoes is the essence of cosmology at the edge. Every method, photometry, spectroscopy, standard candles, standard rulers, lensing, variance, translates whispers into knowledge. None give completeness, all leave uncertainty. But together they form a map, partial yet profound, of a universe seen only in fragments. The cosmos offers itself reluctantly, in faint photons scattered across time. It is our task to listen patiently and without expectation to the echoes that arrive. When light travels across billions of years, it does not always move in straight lines. Gravity bends it, curving its path as though space itself were a lens. This effect, predicted by general relativity and confirmed repeatedly in observation, allows mass to shape vision. Gravitational lensing becomes most striking when galaxy clusters bend the light of galaxies behind them, producing arcs, rings, or even multiple images of the same source. In these distortions lies both complication and gift. They complicate interpretation, for shapes and brightness are altered, yet they also extend reach, magnifying objects otherwise too faint to be seen. Lenses allow glimpses of galaxies at the very threshold of visibility. Gravitational lenses are natural telescopes, instruments built not by human hands but by the geometry of mass. The poetic detail is that lensing can turn a single faint galaxy into a luminous arc stretching across the sky. The arc is not the galaxy itself but a distorted reflection, a mirage created by curved space. Sometimes the same galaxy appears in multiple places, its light taking different paths around the intervening cluster. Each path has a different length, so the light arrives at slightly different times. This means we can see the same event more than once, delayed echoes of the same source. The irony is soft but profound. Time itself becomes fractured by gravity, allowing the same moment to reach us repeatedly. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. Strong lensing, where multiple images and arcs are formed, is rare but spectacular. Weak lensing, subtler and more common, stretches the shapes of many background galaxies slightly, almost imperceptibly. By measuring these distortions across wide fields, cosmologists map the distribution of dark matter, which reveals itself through its gravitational influence, though it emits no light. Weak lensing thus transforms faint statistical patterns into a map of the invisible. Like mist thinning just enough to reveal a shoreline, then stopping, the distortion of galaxies outlines mass otherwise unseen. The irony is that distortion, usually a hindrance, becomes the very tool of discovery. Microlensing occurs on smaller scales, when individual stars or planets pass in front of background sources. These events cause temporary increases in brightness, revealing objects too dim to detect otherwise. In this way, lensing not only probes galaxies at the edge of the universe, but also uncovers planets and black holes within our own galaxy. The bending of light is universal, affecting every scale, from the smallest of stellar remnants to the largest of cosmic structures. It is a quiet demonstration that gravity, though invisible, leaves its trace in vision itself. The mystery lies in how lensing complicates interpretation of the most distant objects. A galaxy seen through a lens may appear brighter and larger than it truly is. Distinguishing its real properties from the distortions requires detailed models of the intervening mass distribution. This modelling is uncertain, for much of the mass is dark and only indirectly inferred. Thus, while lensing extends sight, it also blurs clarity. The irony is that in order to see more, we must accept distortion. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. Another irony is that lensing can act as both window and curtain. It magnifies some galaxies into visibility while hiding others behind the glare of stretched arcs. The sky becomes a collage, with some regions enhanced and others erased. The image of the cosmos is filtered by mass, shaped by distributions we do not fully know. Every map is partial, every vision mediated. The universe shows itself not directly, but through the glass of gravity. The poetic resonance is that lensing reminds us there is no straight path in the cosmos. Every photon has passed near masses that bent its course. This sky is not a perfect record of position, but a projection shaped by gravity. Even the most careful images are interpretations, reconstructions of light that has been deflected, delayed, and distorted. Like echoes in a canyon, the signals are true but altered by the landscape they cross. Lensing also offers glimpses of galaxies from epochs otherwise unreachable. When light is magnified by a factor of tens or hundreds, galaxies at redshifts beyond 10 can be detected. These magnified sources reveal the early stages of star formation, the presence of heavy elements, and the beginnings of structure. Without lensing, they would remain hidden. The irony is that chance alignments of mass and light reveal what even the most advanced telescopes cannot. Nature provides instruments beyond design, though never without ambiguity. The mystery extends further into predictions. Some lenses produce multiple images of the same supernova or quasar, with light arriving years apart. Observing such events allows cosmologists to measure the expansion rate of the universe with independent methods. Yet these measurements often yield values in tension with other approaches, a discrepancy still unresolved. The silence of agreement is missing, replaced by discord between methods. Whether this tension is a hint of new physics or a reflection of overlooked complexities remains uncertain. Silence carries more data than noise, and here the absence of harmony becomes evidence in itself. Three soft ironies recur: visible, yet forever out of reach. The galaxies magnified by lensing are seen more clearly but still remain inaccessible across billions of light years. Only took 13 billion years to arrive. The arcs and rings are delayed visions, photons bent and stretched by immense masses. Silence carries more data than noise. The distortions themselves, once dismissed as confusion, now provide the richest maps of invisible matter. These refrains echo through every observation, each time a lens reshapes our sight. Thus, gravitational lenses expand the horizon of perception, turning mass into telescope, distortion into clarity, delay into knowledge. They're reminders that space is not empty but structured, that gravity sculpts not only orbits and clusters, but also the very paths of light. To contemplate lensing is to accept that nothing is seen in isolation, that every photon is bent by the weight of the cosmos. The edge of the observable universe is reached not directly but through these lenses, which magnify faint galaxies into temporary presence before they fade again into silence. When astronomers attempt to describe the universe, they face a problem that no increase in data can ever remove. There is only one cosmos, only one observable sphere, and only one vantage point from which to study it. This limitation is known as cosmic variance. In practice, it means that some questions about the larger scales cannot be answered with certainty, because there is no possibility of repeating the experiment elsewhere. A sample size of one cannot be enlarged. No matter how carefully maps are drawn, they represent only our horizon, only our sky. The irony is that the grandest questions remain most uncertain precisely because the universe is singular, visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. The poetic detail is that cosmic variance appears most clearly in the study of the cosmic microwave background. The lowest order fluctuations, large patches of slightly hotter and colder regions, are few in number. They can be measured only across the sky we see. If another universe or another horizon existed, its fluctuations might differ. But we cannot compare. Our one view is both evidence and limit. The quiet irony is that uniformity across the sky may be partly truth and partly chance, but there is no way to separate the two. This limitation extends to measurements of galaxy clustering. Large-scale surveys reveal filaments, voids, and superclusters, the cosmic web woven by gravity. But the exact distribution we see may not be representative of the whole. Another horizon might show different structures. The statistics we use to describe clustering are valid within our view, but uncertain beyond it. Like mist thinning just enough to reveal a shoreline, then stopping, the maps end at the edge of vision, and we cannot know if the unseen shoreline resembles the visible one. The mystery is how much of our cosmology is shaped by this single perspective. When we say the universe is flat, homogeneous, and isotropic on large scales, we base it on what we can see. The assumption of the cosmological principle, that the universe is the same everywhere, cannot be proven beyond our horizon. It is an inference, not an observation. The irony is that the simplest and most fundamental assumptions are the least testable. Visible, yet forever out of reach, only took 13 billion years to arrive. Silence carries more data than noise. Cosmic variance also affects attempts to measure the expansion rate of the universe. Different methods yield values that do not entirely agree, a discrepancy known as the Hubble tension. Some of this may be due to measurement errors or astrophysical complexities, but some may be due to the particular region we occupy. If local structure differs subtly from the cosmic average, it could bias our estimates. The universe we see is both sample and anomaly. We cannot step outside to measure again. The poetic resonance is that every direction in the sky is both truth and accident. The patterns of galaxies, the alignments of fluctuations, the distribution of voids, all are real, but they may not represent the cosmos beyond our reach. To map them is to map our horizon, not the whole. This limitation is not a failure of science, but a reminder of perspective. Like standing on a shore and watching waves, one may describe the sea but never the entire ocean. There is irony in how precision deepens awareness of variance. The more accurate our instruments, the more clearly we see the boundaries of certainty. Satellites like Planck have measured the cosmic microwave background with exquisite precision, yet the largest scale anomalies, cold spots, alignments, remain ambiguous. Are they genuine features of the cosmos, or statistical flukes due to our one sample? Precision has not resolved the ambiguity, it has sharpened it. Silence carries more data than noise. Another irony is that even silence itself is affected by variance. The absence of signal at certain scales may be as meaningful as its presence, but we cannot know if that absence is universal or local. The cosmos may be quiet in ways that only we perceive. Another horizon, if it could be observed, might sing a different pattern. Yet the silence we hear is the only silence available. The mystery deepens when considering inflation and the larger universe beyond our horizon. If inflation occurred, then the universe may extend far beyond what we can see, perhaps infinitely. In that case, our observable patch is a tiny fragment of a vast expanse. Variance then becomes not just a limitation, but a profound reminder of scale. The patterns we measure are real, but they are not the whole. The irony is that cosmology is both the most global of sciences and the most provincial, restricted forever to a single sphere. Visible, yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. The poetic detail is that even within this limit, patterns still emerge. The cosmic web shows a universality in its filaments and voids. The microwave background shows statistical distributions that match predictions of theory. The silence of variance does not erase coherence, it only restrains certainty. Like mist thinning just enough to reveal a shoreline, then stopping, variance allows knowledge but not completeness. Three ironies echo softly again. Visible yet forever out of reach. The cosmos we see may not match the cosmos beyond. Only took 13 billion years to arrive. The photons we detect represent a single history, not a universal one. Silence carries more data than noise. The lack of multiple samples is itself a constraint that guides theory. These refrains remind that science is not about completeness, but about honesty in the face of limits. Thus, cosmic variance is both obstacle and truth. It reminds us that observation is bounded, that knowledge is partial, and that humility is as necessary as measurement. The universe is singular, and its singularity defines the edge of certainty. To contemplate cosmic variance is to accept that we live within one horizon only, unable to compare, unable to repeat, yet still able to listen. The cosmos speaks once, not twice, and we must build understanding from that solitary voice. When one speaks of the edge of the observable universe, it is tempting to imagine a boundary, a line beyond which nothing exists. Yet the truth is subtler. The observable universe is not an edge of being, but an edge of seeing, defined by the distance light has travelled since the beginning of cosmic time. Beyond it, the universe almost certainly continues, vast and unbroken. There is no physical wall, no curtain of matter, no frontier at which galaxies end. There is only the horizon of observation, which expands slowly as light from more distant regions arrives. An edge that is not an edge is the paradox at the heart of cosmology. The poetic detail is that this horizon is personal to each observer. Every point in space has its own observable sphere centered upon itself. To an observer in a galaxy billions of light-years away, the horizon encloses a different set of galaxies, different structures, different light. The observable universe is not a shared boundary, but a collection of overlapping perspectives, each defined by position and time. The irony is that while the cosmos is one, its edges are many, visible yet forever out of reach, only took 13 billion years to arrive. Silence carries more data than noise. The difference between the observable and the unobservable is not qualitative but temporal. Galaxies beyond our horizon are no different in kind from those we see. They are simply too far for their light to have reached us. As time passes, the particle horizon expands and more becomes visible. Yet the acceleration of expansion ensures that some regions will never enter sight. The observable grows, but the unobservable grows faster. The horizon is not fixed, yet it is always incomplete. The irony deepens in the fact that the universe may be infinite, or at least vastly larger than the observable region, but we can never confirm it. All that can be studied directly is the finite sphere defined by light travel time. The cosmological principle assumes that what lies beyond is similar to what lies within, but this assumption cannot be tested. Like mist thinning just enough to reveal a shoreline, then stopping. The cosmos reveals itself only partially, leaving the rest to inference. The poetic resonance is that every image of the universe, maps of galaxies, charts of fluctuations, models of structure, is a map not of the whole, but of the horizon. Cosmological surveys chart billions of galaxies, yet these billions are still within a finite bubble of sight. The bubble expands slowly, but the edge remains. To contemplate the observable universe is to contemplate both presence and absence, both what is seen and what is withheld. The mystery lies in what lies beyond. If inflation occurred, then the universe is much larger than we can observe, perhaps infinitely so. It may contain regions with the same physical laws and structures, or it may contain regions fundamentally different. But no signal from beyond the horizon can reach us. The question is therefore beyond the reach of science as currently practiced. The irony is that the most natural question, what lies beyond, is the least answerable. Visible, yet forever out of reach, only took 13 billion years to arrive. Silence carries more data than noise. Another irony is that the edge of the observable universe is different for every epoch. For an observer 1 billion years ago, the horizon enclosed a smaller sphere. For an observer 1 billion years in the future, it will enclose a larger sphere, though accelerated expansion will limit its growth. The observable universe is not a fixed structure, but a moving horizon, changing with time. It is an edge that is never the same, a boundary that shifts as cosmic time flows. The poetic detail is that this horizon is spherical, surrounding us equally in every direction. No matter where one looks, the edge is the same distance away. The symmetry is not because we are central, but because the universe is uniform on large scales. Every observer sees themselves at the center of their observable sphere. The irony is that the cosmos places everyone at the center of their own horizon, not through privilege but through geometry. Even within our horizon, much remains unseen. Dust obscures distant galaxies, noise masks faint signals, and some light is redshifted beyond current detection. The observable universe is itself only partly observed. Our maps are incomplete, our surveys limited. The horizon is not the only edge. There are edges of sensitivity, of wavelength, of exposure, like mist thinning just enough to reveal a shoreline, then stopping. Observation halts long before the horizon itself. 3 soft ironies echo again. Visible, yet forever out of reach. The horizon defines what can be seen, not what can be touched or reached. Only took 13 billion years to arrive. The light that defines the boundary is ancient beyond reckoning. Silence carries more data than noise. The absence of information beyond the horizon is as meaningful as the presence within. These refrains accompany every discussion of the observable universe, gentle reminders of the difference between knowledge and completeness. Thus, the edge of the observable universe is not an edge at all, but a perspective, a limit of vision defined by time, distance, and expansion. It is both finite and infinite, both personal and universal, both shifting and enduring. To contemplate it is to accept that the cosmos is larger than observation, that every map is partial, that every horizon conceals as much as it reveals. The universe continues beyond sight, silent and unbroken, an edge that is not an edge. Beyond the particle horizon lies a silence that no telescope can penetrate. The light from those regions has not had time to reach us, and by definition it never will. What lies beyond the curtain remains hidden, and yet theory insists that it exists. The observable universe is only a patch, and the greater cosmos continues outward, unbounded by our sight. Unknown beyond the curtain is not a void, not an absence of reality, but an absence of access. The irony is that we can be certain it is there, but uncertain of what it contains. Visible, yet forever out of reach, only took 13 billion years to arrive. Silence carries more data than noise. The poetic detail is that this unseen expanse is implied by the very uniformity of what we can see. The cosmic microwave background looks the same in every direction, suggesting that conditions extend smoothly beyond our horizon. The large-scale distribution of galaxies forms webs and filaments that appear unbroken. Everything we observe hints at continuation, like mist thinning just enough to reveal a shoreline, then stopping. The visible universe suggests but does not reveal the greater whole. The mystery is whether the regions beyond mirror our own, or diverge in ways we cannot imagine. Inflationary models suggest that the universe extends vastly, perhaps infinitely, with the same physical laws everywhere. Yet some models allow for variation, domains with different constants or structures. These possibilities cannot be tested, for no light or signal can cross the boundary. The irony is that we build models of the unseen with confidence, while knowing we will never confirm them. Another irony lies in the nature of time. We describe the horizon as a limit of distance, but it is also a limit of age. The universe is finite in its visible past, 13.8 billion years, yet it may be infinite in its extension. The horizon is not the end of space, but the end of memory. What came before recombination? What came before inflation? What lies outside our causal sphere? These remain outside observation. This silence of the unseen is the silence of time itself. The poetic resonance is that cosmology holds two truths at once. The universe is vast beyond measure, and the universe is known only through a narrow cone of vision. We look outward and see billions of galaxies, yet we also know this is only a fraction of the whole. To contemplate this is to dwell in humility. The cosmos is both generous and withholding, revealing enough to suggest its immensity, while concealing enough to preserve its mystery. The unknown beyond the curtain is also hinted at by gravitational waves. Unlike photons, these ripples in space-time are not scattered by matter, and in principle they could carry information from earlier times than light can. Detectors such as LIGO and future space-based observatories may one day register primordial gravitational waves, imprints of inflation itself. Yet even these waves will be limited, constrained by horizons of their own. No signal can cross the absolute boundary of causality. Silence carries more data than noise. The absence of waves from beyond the horizon will speak as clearly as their presence. The irony grows sharper when considering how much of what we know is indirect. We infer the unseen from the seen, projecting patterns beyond the horizon. The cosmic microwave background is smooth, so we imagine smoothness beyond. The distribution of galaxies is web-like, so we imagine filaments extending further. These inferences may be correct, but they may also hide surprises. Perhaps the unseen cosmos is different, but if it is, we will never know. The curtain is permanent, the horizon absolute. The poetic detail is that even the observable itself is temporary. As dark energy drives accelerated expansion, regions we can see today will slip beyond the event horizon. The cosmos we observe is not static but eroding, its visibility shrinking with time. The curtain will move inward, not outward, hiding galaxies that now shine. What lies beyond is not only the unknown of distance, but the unknown of time, the loss of what is now visible. Three ironies echo here again. Visible, yet forever out of reach. We see the evidence of continuity but cannot touch it. Only took 13 billion years to arrive. The photons that form our horizon tell us of a finite past, not of the whole. Silence carries more data than noise. The lack of signals from beyond is itself the boundary of knowledge. These refrains remain constant, as enduring as the horizons they describe. The mystery beyond the curtain is also philosophical. What does it mean to describe something that can never be observed? Cosmology accepts the unseen because its presence is implied by theory and consistency. But whether the unseen belongs to science or to imagination is a quiet question. The cosmos itself does not answer. It continues beyond, indifferent to our categories. The edge of observation is not the edge of existence. The universe goes on, whether known or not. Thus, what lies beyond the curtain is the most enduring silence in cosmology. It is the realm of absence, the infinite remainder, the unreachable whole. To contemplate it is to rest in uncertainty, to accept that knowledge has limits. The universe teaches not only what is, but also what cannot be known. It offers sight up to a point, and beyond that it offers silence, and in that silence there is a truth of its own, a truth that knowledge must coexist with mystery, and that the greatest edge is the one that will never be crossed. At the farthest edge of contemplation, where the observable meets the unobservable and where knowledge thins into silence, the narrative slows into stillness. Thinning into stillness is not a description of absence, but of presence so faint that it feels like quiet. The universe is spoken through light, through redshift, through scattering and fluctuation, and at the limit it withdraws into darkness once more. The cosmic microwave background marks the beginning of visibility, but beyond it lies opacity. The particle horizon marks the extent of contact, but beyond it lies separation. The event horizon marks the future of reach, but beyond it lies isolation. In every direction the horizons converge on a single truth. What we see is partial, and what remains unseen is greater. The poetic detail is that silence at the edge is not emptiness, but potential unmeasured. The sky is filled with photons that never arrived, galaxies that will never appear, structures that will never be mapped. Absence is abundant, overflowing with what lies beyond. Like mist, thinning just enough to reveal a shoreline, then stopping, the edge of the observable universe reveals only a fraction of what is there. It is a shoreline glimpsed but never walked upon, a distance forever visible but never crossed. The irony is soft and repeats in rhythm, visible yet forever out of reach. The galaxies at the horizon shine in ancient light, but the galaxies themselves have moved far beyond. Only took 13 billion years to arrive. The photons we see today are delayed memories of an earlier universe, their sources long changed or gone. Silence carries more data than noise. The gaps, the erasures, the absences at the horizon are the most profound truths the cosmos has to offer. These ironies accompany every attempt to describe the edge, turning limitation into insight. The mystery remains in what lies beyond. Inflation suggests vast regions, perhaps infinite, stretching outward without bound. Yet no observation can confirm it. Dark energy ensures that much of what we see will vanish beyond reach, leaving future observers with emptier skies. Gravitational waves may carry whispers of earlier times, but they too are finite. The curtain is not a failure of instruments, but a property of reality. To reach the edge is to meet the laws of physics themselves, and those laws leave part of the universe forever unseen. The poetic resonance of this realization is that cosmology itself is an act of patience. Every photon that arrives has travelled across silence, across billions of years of expansion, across collisions and absorptions and redshifts. They arrive not in rush but in trickle, faint and delayed. To study them is to listen slowly, to measure absence as carefully as presence. The cosmos teaches patience by its very nature. It does not give itself at once, but only across time, only through echoes, only in fragments. Another irony is that as instruments grow more powerful, as telescopes reach further and deeper, the horizon remains. It recedes, but it never vanishes. Each advance reveals more galaxies, more structure, more detail, but always within the sphere of the observable. Beyond it, the unknown endures untouched. Knowledge grows, but mystery grows with it. The edge is both pursued and preserved, visible yet forever out of reach. Only took 13 billion years to arrive. Silence carries more data than noise. The quietest truth of the edge is that it is not final. The observable universe is a concept tied to time, and as time flows, the horizon changes. Every moment allows new light to arrive, expanding the sphere of vision. Yet expansion also drives galaxies beyond the event horizon, ensuring that even as new regions become visible, others slip away. The cosmos offers and withdraws at once, balancing revelation with concealment. like mist thinning just enough to reveal a shoreline, then stopping. The horizon opens just far enough to suggest what lies beyond, and no further. The poetic detail is that even in silence there is continuity. The laws of physics apply equally beyond the horizon. The unseen is not alien but kin to the seen. Galaxies beyond our reach follow the same rules, shaped by the same forces, lit by the same processes. The unknown is not unknowable in principle, only unreachable in practice. The horizon is a wall of perception, not a wall of existence. The universe does not stop where our vision stops. The final irony is that in contemplating the edge, one also contemplates the center. Every observer, no matter where, sees themselves at the middle of their observable sphere. The cosmos places all in the same apparent position, not through privilege but through geometry. This universality is itself a truth. The cosmos is impartial, each observer enclosed in their own horizon, each horizon expanding and receding in equal measure. What feels central is shared by all. The universe is democratic in its limits, and so the narrative slows, not into conclusion but into stillness. The light that has travelled longest fades into silence. The horizons that define knowledge remain, drawn not as walls but as distances. The mysteries that lie beyond persist, untouched by vision but acknowledged in thought. At the edge of the observable universe there is no final revelation, no sudden closure, only the soft quiet of absence. The cosmos rests beyond, unbroken and unobserved, and we rest within, gazing outward until vision thins into stillness. The story of the observable universe does not end at a boundary. It dissolves. Horizons blur into silence, distances stretch into absence, and light thins until it becomes almost indistinguishable from darkness. The farther one looks, the more the cosmos withdraws, leaving only faint echoes and scattered photons. Beyond those echoes lies continuation without witness, a universe that endures whether seen or not. The observable edge is not a wall, but a soft fading, a mist that allows glimpses before it conceals again. The poetic detail is that this fading is not loss, but rest. Every photon that has travelled across billions of years has fulfilled its journey in reaching a detector, in leaving its record on the night sky. Those photons that never arrive remain part of a silence that is no less complete. Like waves on a shore, some reach the sand, others break before they arrive, but the ocean remains whole either way. The cosmos is not diminished by what is unseen. The irony persists quietly, visible, yet forever out of reach. Horizons enclose us in a sphere of memory but not of presence. Only took 13 billion years to arrive. The light that appears ordinary is the long-delayed voice of ancient fire. Silence carries more data than noise. Absence itself is a form of knowledge, a reminder of where sight cannot go. These truths soften into rhythm, repeating until they feel less like limitations and more like lullabies. Time stretches outward, galaxies recede, and the universe continues beyond our vision. Yet within the observable sphere lies enough vastness to occupy thought without end. The curtain may conceal infinity, but the finite sky is already immeasurable in its depth. To dwell on its edges is to learn patience, to accept that knowledge is partial, and to rest in the quiet balance of presence and absence. The rhythm slows further, words trailing into silence. Horizons drift outward without being chased. Light fades without being sought. The cosmos remains vast and unbroken, yet for now it rests, and so do we.